Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section P4 on multiplying polynomials and rationalizing binomial denominators. So before we get started, let's make sure we're all comfortable with the terminology surrounding the polynomials that we're going to be working with in this section. We say that if n is a non-negative integer and we have a series of real numbers, a0 through an, because those are going to be our coefficients, then a linear combination, we sometimes call it, of powers of x represents a polynomial. And a linear combination is basically a fancy way of saying a constant times what you're talking about, plus or minus a constant times what you're talking about, so on and so forth. So it's just constants times the power of x, plus or minus a constant times the power of x. And in this case, we say that this is a polynomial in just one variable x, because when you get to higher level math, you might have polynomials that are in terms of multiple variables. Now, there are some parts of this polynomial that are so important that we have special language around it. So n, which in this case is the stand-in for what represents the highest power of x in the polynomial. So the highest power of x is called the degree of the polynomial. So if you had something like 3x to the fifth plus 4x squared plus 2, this would be a polynomial of degree 5 because the highest power of x that you have is 5. Now, when we're writing these polynomials, we usually write them in order from the biggest power of x to the smallest. The reason we do that is just to make it easy to read. It doesn't make it wrong if it's not in that order. The degree is still the highest power of x regardless. So if you had something like instead 2x plus 4x cubed minus 2, then the degree of this polynomial would be 3, which we have a special name for as well that we'll get to in just a minute. So we say that a first degree polynomial is called a linear polynomial. So a first degree means that the highest power of x is 1. So you might have something that looks like 3x plus 2, which if you've had high school algebra, which hopefully everyone has, you might recognize as something of the form mx plus b. So it's called a linear polynomial because a polynomial of degree 1 is a line, mx plus b. A second degree polynomial, so the biggest power of x is 2, is called a quadratic polynomial. We'll talk quite a bit more about those later on in the course. And then a third degree polynomial, like the one up here, where the highest power of x is 3, is called a cubic polynomial. Now, occasionally you'll hear people use shorthand for polynomials of degrees a little bit bigger than 3. For example, a degree 4 polynomial is sometimes called a quartic polynomial, but most of the time, honestly, once we get beyond a power of 3, we just use the number. So we would say a 4th degree polynomial, a 6th degree polynomial, so on and so forth. All right, so again, the degree is just the highest power of x. The coefficient of the highest power of x, which is represented by the constant a sub n in this generic notation, is called the leading coefficient. And the leading coefficient is actually very important and tells us a lot about the polynomial itself, which is why it has a special name. We'll get a little bit of taste of that once we start talking more about polynomial, or rather quadratic functions, later on in the course. So in this example we have up here, since the highest power of x is this x cubed, a positive 4 would be the leading coefficient of this polynomial. If you write them in descending order, of course, the leading coefficient will always be the constant out front. And then last but not least, a sub 0, the final term that doesn't have a power of x after it, you could think of that as the x to the 0th term by properties of exponents, because x to the 0 is just 1. That is called the constant term because it's exactly that. It's just a constant. Plus 3, minus 2, plus 7, so on and so forth. A little bit more language that we're going to use to reference some of the things we're working with in this section is terminology based around the number of terms you have in your polynomial. And this has nothing to do with the degree anymore. That's a very important distinction. So we say that polynomials with 1, 2, and 3 terms are called monomials, binomials, and trinomials respectively. Monomial with the prefix mono for 1, binomial with the prefix bi for 2, and trinomial with the prefix tri, of course, for 3. So I've got some examples of all of those down below. So examples of monomials, you might have x squared, you might have 3x to the 4th, you might have negative 2x to the 10th. Again, these are all different degree polynomials. The degree doesn't matter. The thing that matters is that they're all just a single term, some constant times some power of x. Similarly, binomials have 2 terms. So you could have something like x squared plus 2, or something like 2x to the 7th minus 3x to the 5th. And then trinomials would, of course, then have 3 terms, regardless of the degree. What we will be primarily focusing on in the first part of this section is multiplying polynomials together, and we're going to start by multiplying binomials together, and then we'll occasionally throw in a trinomial as well to show how it changes. All right, so let's start by multiplying 2 binomials together. And a lot of students learn this as the process called FOILing, which is a good way to think about it. This basically tells you how you multiply them together. The F in FOIL stands for the first. You multiply the first terms times each other. So in this case, it would be a times a, which is a squared. The O stands for the outer terms. So that would be a times negative 2, which would be negative 2a. The I stands for inner terms. Positive 9 times a would be a plus 9a. And then the L in FOIL stands for the last terms, the second in each pair. And so that would be 9 times negative 2 for a minus 18. In this case, the 2 terms in the middle are similar. They're both a to the first power, so we can combine them together to get a squared. A plus 9 minus 2 would give us a plus 7a minus 18. Right, foiling is a good way to think about it, but it's important that you pay attention to what's actually happening here and understand the mechanics behind it so that we see how it generalizes once we start dealing with larger polynomials as well. And essentially, it's just distribution by parts. So to begin with, you distribute the a in the first binomial through both parts of the second binomial. That's the F and the O in FOIL. And then you distribute the second term, the 9, through both parts of the second binomial. That's the I and the L in FOIL. So it's really just distribution, a step at a time. All right, so for part B, we're asked to find 2x plus 5 quantity squared. Please, 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 do not think of that as 2x squared plus 5 squared. I will be very, very unhappy if I see this mistake. Exponents distribute across multiplication and division. We addressed that in section P3. They do not distribute across addition and subtraction. We wouldn't need to FOIL if that was the case. So what we're going to do in this case is, because anything squared by definition is just multiplied by itself, is we're going to write this out. This is 2x plus 5 times itself, 2x plus 5. And then at that point, you just FOIL it, same as part A. So I'm going to distribute the 2x through to both parts. 2x times 2x, you can multiply the 2's together to get 4. Multiply the x's together to get x squared. And then we would have 2x times the 5, which would give us a plus 10x. Then we're going to distribute the 5 through both parts. So 5 times 2x would give us another 10x. And 5 times 5 would give us 25. And then once again, we can combine the 2 terms in the middle, because 10x plus 10x would give us 20x. All right, so if you just try to imagine distributing the exponent through and squaring both pieces, you actually miss out on this middle term. You do not get the correct answer. Do not distribute exponents across addition and subtraction, please. So now we're going to work part C and D of example 1, more multiplying polynomials together. But in part C, we now have a binomial times a trinomial. And the idea of it is still the same. You're just going to take each piece of the first polynomial and distribute it completely through the second polynomial. So I'm going to start by multiplying everything in the second one by 2x, distribute the 2x through, and then I'm going to distribute the minus 1 through. So we're actually going to end up doing 6 multiplications in total in this case. So let's start with the 2x. To begin with, we're going to have 2x times 4x squared, which would give us 8x cubed. Then we're going to get a 2x times a 2x, which would give us a 4x squared. And then 2x times a positive 1 would give us a plus 2x. Then the second one's going to be easy because the minus 1 just makes everything negative. So that would give us a minus 4x squared minus 2x minus 1. And so we're going to have a couple of common terms we can combine together here. We've got 2x squared terms. So we only have the 1 cubed. So the 8x cubed just carries down. But then the 4x squared and the minus 4x squared actually just cancel each other out. They subtract each other away. So those are gone. Then we've got two terms with x to the first power in it. And those are also opposites. We got a plus 2x and a minus 2x. So those cancel each other out. And so all we're left with is the final constant term of minus 1. And then last but not least, for part D, we've got 2x to the mth power minus 1 times 2x to the mth power plus 1. So this is just foiling again. Binomial times a binomial, but now we're going to have to use properties of exponents a little bit more because we're dealing with variables in the exponent instead of numbers. Although we're technically just using the same properties of exponents, you actually just have to think about it a little bit differently. So to begin with, first terms, 2x to the m times 2x to the m. Well, let's think about what that would do. The numbers are easy. 2 times 2 is 4, but what about x to the m times x to the m? So there are actually two different ways to think about this. Both will get you to the same result. The first is to think of this as x to the m plus m. You're multiplying two things with the same base together, which is what we do when we do, say, x to the first power times x squared gives us x cubed. Same idea. But m plus m you can also simplify, and you can write that as 2m. The other way to think about it, which will get you to the same result, is that x to the m times x to the m is x to the m squared, which by property of exponents is also x to the 2 times m. But either way, that's going to give us 4x to the 2m. And then we're going to have 2x to the m times a positive 1. So a plus 2x to the m. And now to distribute the minus 1 through, negative 1 times 2x to the m would give us a minus 2x to the m. And minus 1 times a positive 1 would give us a minus 1. Note that the two terms here in the middle, 2x to the m and minus 2x to the m, cancel each other out. They're the same but opposite, one positive, one negative. And so what we end up with in this case is 4x to the 2m minus 1. Now the two terms in the middle here canceling out was not a coincidence. It turns out anytime you multiply what are called conjugates together, conjugates are when you have the same two terms, 2x to the m and 1 in this case, but the sign in the middle is opposite, then it will always line up so that those two middle terms cancel. Let's prove this by doing it in the abstract. Let's say we multiply a plus b times a minus b and see what happens. Well, by foiling, we would get a squared minus ab plus ab minus b squared, because it's a positive b times a negative b. So minus b squared. And so the middle terms cancel out, and you'll always just get a squared minus b squared. That's actually a really important concept that we're going to come back to in a little bit, because we're going to take advantage of this to get rid of square roots in denominators in a few minutes. For the second type of problem in this section, here in example 2, we're going to combine multiplying polynomials together with the radical properties that we were looking at in section P3. So we're going to start adding roots into the mix. So try pausing the video here and see if you can find the solutions to example 2 parts A and B. All right, so again, it's just foiling when all is said and done. For the first term, or for part A rather, we would get 5 times 4, which would give us 20. 5 times a negative 3 square roots of 2 would give us a minus 15 square roots of 2. If you're a little bit confused with that, make sure you go back and brush up on section P3, because we talked about the way that works with multiplication being commutative, so we can basically multiply like terms together. And then for the square root of 2, we have square root of 2 times 4, so that would give us just 4 times square root of 2. Can't do much with that. And then we've got a square root of 2 times a minus 3 square roots of 2. So let's think about what's happening there. Square root of 2 times a negative 3 square roots of 2. Well, the minus 3 is just going to stick around because there's no constant to multiply it with, but we can do square root of 2 times square root of 2. Remember, properties of radicals, square root of a times square root of b is square root of a times b. So that would be minus 3 times the square root of 4, or, because square root of 4 is just 2, negative 3 times 2. The other way to think about that is square root of 2 times square root of 2 is square root of 2 squared, and then the square root and the square cancel each other out. But either way, this is going to be a property we run into a lot in this section, so just keep that in mind. Square root of a times square root of a just cancels out the square root. You just get the a left over. And so this is going to give us a negative 3 times 2, or a minus 6 for our final term. Now we're not quite done yet, because again, properties of radicals, operations with radicals from the previous section, because these are both square roots of 2, like radicals, we can combine those middle terms together still. And on top of that, we've got 2 constants as well that we can also combine together. So let's start with the square roots. We've got a minus 15 square roots of 2 plus a 4 square roots of 2. So minus 15 plus 4 would give us a negative 11 square roots of 2. And then we've got a 20 minus 6, which would leave us with a plus 14. Now, if you had worked this problem and put your answer in the reverse order, positive 14 minus 11 square roots of 2, that would be the same thing and equally acceptable. What you do want to be a little bit careful about, or just you'll get used to it with a little bit of time, is that it is important that you put constants in front of square roots just to make sure there's no confusion. So I would never write square root of 2 times 11 like this, because at that point it gets a little bit fuzzy as to what's under the square root and what's not under the square root. So it's just always standard procedure to write the constants like coefficients, put them in front of the square roots. Similar for part B, the only difference is we have just more square roots to work with. So in this case, FOIL again. So we're going to have 2 square roots of 6 times 4 square roots of 6. So if we multiply the constants together, 2 times 4 would give us 8. And then again, this happens a lot. Square root of 6 times square root of 6 is just 6. And so now we can also multiply those together, which I will do in the next step. Next up, we've got 2 square roots of 6 times a negative square root of 3. So that would be a minus 2. And again, properties of radicals, square root of 6 times square root of 3 is square root of 6 times 3, or square root of 18. Next up, we've got a negative square root of 3 times 4 square roots of 6, which will give us a minus 4 square roots of 18. And then we've got a negative times a negative, which is going to turn this into a positive, square root of 3 times square root of 3, which again is just 3. So again, lots of like terms here. I'm going to do some simplification. So 8 times 6 would give us 48. Square root of 18 we can actually simplify because 18 is 9 times 2, a perfect square. So that's 3 square roots of 2. So for this first term, if we've got a negative 2 times 3 square roots of 2, I'm going to basically go ahead and multiply this negative 2 into this. That's going to turn this into a minus 6 square roots of 2. Similar for the next term, this is going to be a 4, and the minus sign is going to stick around out front, times 3 square roots of 2. And so the 4 times 3 would give us 12 square roots of 2. And then we have the plus 3 on the end. And then once again, we get pairs of like terms. 2 with square root of 2, and 2 that are just constants. So let's do the constants first this time. Why not? Just to mix it up. So we would have a 48 plus a 3, which will give us a 51. And then a minus 6 times a minus 12 would give us a minus 18 square roots of 2. All right, 2 more to illustrate a point. So once again, try pausing the video and see if you can find the solutions to part C and D of example 2. So for part C, once again, it's just FOILing. So we will get square root of 2 times square root of 2, which is just 2. 5 times square root of 2 would be a plus 5 square roots of 2. Minus 5 times square root of 2 would be a negative 5 square roots of 2, and then a negative 5 times a positive 5 would give us a negative 25. But if you notice what happens in the middle here, we have a positive 5 square roots of 2 minus 5 square roots of 2, so those cancel. So this is just 2 minus 25, or a negative 23. It shouldn't be that surprising that the middle terms cancel because, again, if you take a closer look at what we just FOILed, these are conjugates once again. They're the same terms, square root of 2 and 5, but with the signs in the middle opposite. And take note of what you see happened here. When we multiplied by the conjugates, our final answer had no square roots in it. That's really important because that's what we're going to do to rationalize binomial denominators with square roots in just a minute. Part D, you have 2 square roots of 5 plus 2 squared. So once again, do not distribute that exponent through, please. Anything squared is times itself. So I'm going to write it out twice and then FOIL it. So 2 square roots of 5 times 2 square roots of 5 would give us 4 for the 2 times 2, and then a 5 for the square root of 5 times itself. So that'll combine to give us 20 in the next step. 2 square roots of 2, or 2 square roots of 5 plus times a positive 2 would just give us 4 square roots of 5. Another 4 square roots of 5, and then 2 times 2 would give us 4. And so this is 20 plus 4, or 24, plus 8 square roots of 5. All right, so now let's get to rationalizing denominators. And we got a little bit of a taste of this in the previous section P3, but in the previous section we always had monomials in the denominator. And if that's the case, you always just multiply by the thing you're trying to rationalize on both the top and bottom of the fraction to make sure you keep it balanced, to not change the value. The same thing still holds here. So for part A, where all we have is a monomial in the denominator, square root of 6, the problem works the same way. We're going to multiply both the denominator and the numerator of the fraction by square root of 6. But be a little bit careful here. Whenever your numerator or denominator has multiple parts like this and you multiply something in, imagine it's in parentheses. because you're going to have to distribute that square root of 6 times the entire numerator. And so that's kind of the thing to watch out for here. So for the top of the fraction, we're going to have square root of 6 times square root of 2, which would be square root of 12, and then plus square root of 6 times square root of 3, which is square root of 18. Note that we could not have combined those together to get square root of 5, because remember, square root of a plus square root of b does not simplify. That is not square root of a plus b. It doesn't work that way. Knowing what you can't do with square roots, and with a lot of things in algebra, it's just as important as knowing what you can do. Now this is all going to be divided by square root of 6 times itself, which is just 6. But we're not quite done yet, because both of those square roots in the numerator can simplify. And we're looking for simplest form, which means simplified radical form. If we can simplify the square roots, we should simplify the square roots. So square root of 12 is 4 times 3, and 18 is 9 times 2. So that's going to give us 2 square roots of 3 plus 3 square roots of 2 all over 6. Now if there was something in common between all of these coefficients, we could reduce the fraction, but since there's nothing in common between 2, 3, and 6 other than 1, which wouldn't get us anywhere, that's as simple as this problem gets. Part B, this time around we've got 3 plus square root of 5 in the denominator. So just imagine that you tackled this problem the same way that we did part A, and think about what would happen. So if all we did was just try to multiply both the top and bottom by square root of 5 to cancel that out, well again, because of the same idea, you would have to distribute that through. So it's true that the square root of 5 would cancel with the other square root of 5 to give you 5, but in the first term, you would now have 3 times the square root of 5. So it wouldn't get you anywhere. So that doesn't work. And that's why whenever you have a binomial with a square root in the denominator like this, we multiply by its conjugate. So if I want to cancel out the square root of 5 and 3 plus square root of 5, I need to multiply by 3 minus square root of 5. Be careful, you don't want to multiply by the same thing, another 3 plus square root of 5. That will not get rid of the square root either. We actually saw an example of that in part D of example 2, where we squared a term with a square root in it, and we still had square roots left over at the end. It's very important that you remember to flip the sign in between. Otherwise, the middle terms won't cancel out. And of course, whatever we multiply the bottom of the fraction by, we still need to multiply the numerator by the exact same thing, 3 minus the square root of 5. So in the top of the fraction, the 2 will distribute through. So we would get 6 minus 2 square roots of 5. And in the denominator, we would FOIL. And I'm going to take a shortcut because I know I can ignore the middle terms. So the first terms would give us 3 times 3 or 9. And then again, we would get a minus 3 square roots of 5 plus a 3 square roots of 5, which would cancel. And then a positive square root of 5 times a negative square root of 5, positive times a negative is a negative, and square root of 5 times itself would get rid of the square root. Now that the square root's gone and we just have constants, we can combine those together. 9 minus 5, of course, giving us 4, but this time around we do have all even numbers in each term in the fraction. So I'm going to be able to reduce this. The biggest number in common that we could divide into all of these is 2. So I'm going to factor a 2 out of the numerator, leaving us with 3 minus 1 square root of 5. And then that will reduce into the denominator, giving us 3 minus the square root of 5 over 2. Now you do not have to go through that process of factoring out the term in common each time, but it is important to remember that when you start dividing everything in the fraction by 2, the 2 that we pull out of this 4 has to divide into both parts of the numerator. It doesn't just reduce with 1. I see this all the time. If I have a problem where I end up with something like 3 plus 2x over x, I'll see students try to reduce this x with this one on top. It doesn't work that way. If that x is going to reduce, there has to be an x in all terms in the fraction. So don't make that mistake. All right, last but not least, we've got part C and D of example 3. So try pausing the video here and see if you can find the solution to these two. Same idea as we had on the previous slide. The only difference is they're throwing more and more terms at us with more and more square roots. So for part C, it's always the denominator that you're trying to rationalize. So it's its conjugate that you multiply by. So to cancel out square root of 2 minus square root of 3, I need to multiply by square root of 2 plus square root of 3. And whatever I multiply the bottom of the fraction by, multiply the top by the same thing. So in the numerator, when we distribute, we would get square root of 6 plus square root of 3 times square root of 3 would just be 3. In the denominator, square root of 2 times itself would be 2. Then we would have a positive square root of 6 and a negative square root of 6 that would cancel. And then for the last terms, we've got a minus times a positive, so a minus square root of 3 times square root of 3, which would just be 3. So this is a square root of 6 plus 3 divided by negative 1. But dividing by negative 1 just changes the sign. So I'm going to go ahead and simplify this. But again, much like on the previous page, that negative 1 is going to divide into both terms of the numerator, changing their signs. So this would give me a negative square root of 6 minus 3. And then last but not least, again, part D here. It's the denominator you're trying to rationalize. Don't multiply by the conjugate of the numerator. That's not going to help. So I want to multiply by 3 minus the square root of 8 on both the top and bottom to keep the fraction balanced. And I essentially just have to FOIL twice here. Once for the numerator of the fraction and once for the denominator of the fraction. So in the top, we're going to get 3 times the square root of 2 minus the square root of 2 times square root of 8, or square root of 16, plus 15 minus 5 square roots of 8. And we can do some simplification with that, but we're going to come back to that in a second. Let's go ahead and FOIL out the denominator as well. And because those are conjugates, we already know that's going to work out nicely. 3 times 3 is 9. The outer and inner terms cancel. 3 square roots of 8 minus 3 square roots of 8. And then we have a positive times a negative, so a minus square root of 8 times square root of 8 would just be 8. Well, that's nice because 9 minus 8 is just 1, and dividing by 1 doesn't change anything. So the denominator essentially we can just drop. 3 square roots of 2 minus the square root of 16 plus 15 minus 5 square roots of 8. But there are certainly some perfect squares that we can pull out of some of these square roots. So let's simplify. Square root of 16, because in fact we don't even have to pull anything out of that, right? Because 16 is already a perfect square. Square root of 16 would just be 4. And then we would have plus 15, and then for square root of 8, since 8 is 4 times 2, we can take the square root of the 4, which would leave us with 2 square roots of 2. The minus 4 plus 15 would give us a plus 11. And then I can multiply the coefficients together to get a minus 10 square roots of 2. And then we can combine those two terms together. 3 minus 10 would give us a negative 7 square roots of 2 plus 11. And again, you could also write that as 11 minus 7 square roots of 2 as well. Same result. All right, and that is it for section P4. Bit of a shorter video this time around to take a little bit of a breather from the longer video of section P3. But don't worry, the next one will go back to being a bit on the longer side again. So this is a much more focused section. There's not a lot of variety in this section. In essence, you really just have 3 types of problems. Make sure you can multiply polynomials together. The biggest you're ever going to run into is a trinomial in this class, but if you ever did have more, the idea of it would be the same. So if you had, say, a binomial times a polynomial with 4 terms in it, you would just distribute the a through to all 4, distribute the b through to all 4. If you had a trinomial times a trinomial, you would distribute the a through to all 3, distribute the b through to all 3, distribute the c through to all 3. So you would end up with 9 terms in total. All right, so really it's just distribution when all is said and done. The second type of problem, make sure you can also multiply binomial expressions involving radicals, and that's really just making sure you're comfortable with multiplying terms with radicals in them together. And then the final type of problem in the section that we worked in example 3 was make sure that you can rationalize denominators with binomials containing square roots. Make sure you know that multiplying by the conjugate is the way to get rid of those square roots. All right, and it is important to note that that technique does only work with square roots. If you add a different degree of root in the denominator, like a cube root, things get much more complicated at that point, and it's beyond the scope of this course. So you'll only ever be asked to rationalize denominators involving square roots, at least binomials with square roots. With that said, as always, if you guys have any questions about the material, please make sure you let me know, and I will see you in the next video.